So I'm leaving the floor to Dr. Shreyasi Mukherjee. Is going to perform a final examination, so I leave the floor to the commission, let's say.
Okay, thank you. So welcome, of course.
Thank you.
And so we give you 25 minutes to make a speech. And after that, we will have 15 minutes discussion section.
Okay.
So I will take the time.
Okay.
So when it is 5 minutes left, I will what is okay?
Okay.
So please start.
Okay. Hi, everyone. So I am Shreyasi Mukherjee. And first of all, I thank the committee and all for being present here. And I thank to my supervisor, Professor Luigi Giannelli. I thank you for everything, especially for being so patient with me. And I also thank to my co-supervisors, Professor Mauro Paternostro from University of Palermo, and Dr. Fabio Cirinnà from Leonardo S.p.A. for their cooperations. And a special thanks goes to our group leader, Professor Falci, who has always been very supportive and encouraging. And at the end, I am also grateful to my family and my colleagues here who made my stay in Italy memorable. So, okay, today I'm going to talk about my thesis titled as Quantum Sensing of Noise Based on Machine Learning. So we know that exploiting coherence properties of quantum systems such as superposition, entanglement is essential for achieving quantum advantage. But the presence of the environmental noise can disrupt these properties as it causes decoherence and thereby reduces the fidelity of quantum operations. We do have some noise mitigation strategies, for example, dynamical decoupling or passive error avoidance, etc. But all these methods rely highly on the knowledge of the noise itself or on the characteristics of the noise. So if we want reliable quantum technology, then noise characterization is essential. Even though single qubit noise characterization has been well established, which led to quantum operations beyond error correction threshold, which have been shown in many different works, but still it's a challenging task in multi-qubit system because here the spatial and temporal correlated noise can really have some detrimental effects. In fact, spatially correlated noise can affect badly quantum error correction, which is one of the pillars of quantum computing. And in the last decade, machine learning has emerged as a great diagnostic tool. And in this thesis work, our goal is to enable a robust noise classification or characterization strategy based on their temporal, spatial, and energy correlations in multi-level quantum systems by combining quantum control and machine learning, especially supervised learning. So I will mainly talk about three main works that we have done during my PhD period. The first one is classification of noise correlations in a three-level system. The second is two-qubit quantum sensor for detection of noise correlations. The third one is detection of noise Gaussianity in quantum systems. And at the end, I will show you the conclusions and discuss some future perspectives. So let's move to the first one, which is classification of noise correlations in a three-level system with machine learning. Here we considered a three-level system with eigenbases 0, 1, and 2. The system is driven by two time-dependent pulses, omega p, the pump pulse that couples the states 0 and 1, and the Stokes pulse, omega s, which couples the states 1 and 2. So we have a lambda system. It is also subjected to diagonal noise, and the parameters here are delta p and delta, which are the single and two photon detunings respectively, and x1 and x2 are two stochastic processes that represents the noise. So basically, the role of the noise here is to induce fluctuations in the energy levels. And based on the characteristics of these two stochastic processes, we will define different noise classes that will eventually be distinguished by the machine learning tool. So to control the dynamics of the system, here we exploit stimulated Raman adiabatic passage, STIRAP, or in quantum dot system, it is called CTAP protocol, which is an adiabatic protocol which allows us to transfer the population from state 0 to state 2 without populating state 1. This protocol is well known for its robustness and high fidelity. And to achieve this efficient population transfer, it is required the two-photon resonance condition, which implies that the parameter delta has to be nearly equal to 0. And then in this case, one of the instantaneous eigenstates states of the system is a dark state, which does not have a component along state 1. This protocol is also based on the application of counterintuitive pulse sequence, which means that first we apply omega S pulse that couples the states 1 and 2, and then while gradually turning it off, we turn on omega P pulse, which couples the states 0 and 1. And in this situation, if the system evolves adiabatically, starting from state 0, then it will always follow the dark state, and that's why the population will be transformed from 0 to 2 without populating state 1. Here I want to point out two things. First, here we define the efficiency of the protocol by the parameter psi, which is the population of state 2 at the end of the time evolution of the system. This parameter is important because later we will see that we will use this to train our machine learning model. And the second point is our main goal here is not to achieve an efficient population transfer, but we are just exploiting this protocol in order to get information about the noise that affects the system. In fact, we will see that we will get more information from the imperfections. So our main goal here is to distinguish among 5 different types of noise with the help of machine learning. Among these 5 types, there are 3 non-Markovian quasi-static noise and 2 Markovian noise. Here, quasi-static implies that both the random variables x1 and x2 remain constant during a single trajectory, but change their values in the next trajectory. And for the non-Markovian noise case, based on their energy correlations, we have 3 subclasses. First, the correlated noise, where x2 is equal to eta x1. The correlation parameter eta here always is positive. The second class is anti-correlated noise, where eta always assumes negative values. And the third class is uncorrelated noise, where x1 and x2 are completely independent of each other. And for the Markovian noise, it is delta correlated in time. And as per the energy correlations, we have correlated and anti-correlated noise. Now, for the non-Markovian noise, okay. Now for the non-Markovian noise, we can, for a single noise realization, we can solve the dynamics of the system using time-dependent Schrodinger equation, and we can calculate the STIRAP efficiency by taking average over all possible realizations of the noise. And for the Markovian case, as the system is ruled by zero mean and delta correlated noise, in this case, we are able to derive a Lindblad master equation, and the efficiency can be calculated using the formula below. And so we propose the following protocol. As we will use supervised learning, which requires label dataset, and to generate this, we apply STIRAP protocol under 3 different driving conditions. When omega p max is equal to omega s max, when omega p max is greater than omega s max, and when omega p max is less than omega s max, where this omega p max and s max are the amplitudes of the pump and Stokes pulses. And the efficiencies calculated under these 3 driving conditions goes as input to the neural network. And of course, the labels are the 5 different noise classes that I already mentioned. And in fact, in the output of the neural network, these are the probabilities that the noise belongs to any of the 5 classes that we have. Now, this is the main result. Here, each diagonal entry represents the percentage of accurate classification, where the off diagonal entries represents the percentage of error. And in the y-axis here, actually, we plotted the true levels of the noise, and in the x-axis, we plotted the predicted levels. And from here, actually, we can get 3 messages. First, that the neural network is able to distinguish very well the non-Markovian and Markovian noise. And the second message is it is also able to distinguish very well, almost with 100% accuracy, the subclasses of the non-Markovian noise, the energy correlations of the non-Markovian noise. And the third message is it fails to distinguish the energy correlations of the Markovian noise. And in fact, we can get an overall classification accuracy of 80%. And if we simply merge the 2 Markovian subclasses and make it a single one, then from the figure right here, we can see that again we achieve an classification accuracy around 99%. And in the figure below here, here we plotted the training history of the neural network, considering both 4 and 5 noise classes with respect to the number of epochs. In the figure left here, we plotted the accuracy, and in the figure right here, we plotted the cost function. Now, until now, we considered the ideal efficiency measurement. Then we were also interested to see how the classification accuracy changes with respect to the finite number of projective measurements. And we saw that around 2000 measurements, it already reaches the accuracy already reaches the ideal case. So even if we have a small statistical error in our measurements, still this methodology works. Now let's move to the second work, which is 2-qubit quantum sensor for detection of noise correlations by machine learning. Here we proposed a design of 2-qubit sensor to detect spatial and temporal correlation of noise by expanding our ideas, which is used in the previous work. And here we have 2 qubits with energies epsilon1 and epsilon2 respectively, and they are coupled with each other by XX Ising interaction. And they are also driven by 2 local fields, W1 and W2, and are also subjected to local dephasing noise. So here then the question arises, is it possible to apply stirrup-like protocol also in this case? So let's first look at the structure of the system. So for simplicity, we considered that the 2 qubits are identical, so they have the same energies. And we can diagonalize the system Hamiltonian into 2 invariant subspaces. One is with even parity, another one is with odd parity. And the corresponding eigenvalues and eigenstates are given in the table here. The even parity states are 0 and 1, and the odd parity states are 3 and 2. And now if we drive the 2 qubits symmetrically, so we have W1 is equal to W2, then the state 3 is uncoupled with the rest, and we are left with 3 levels, 0, 2, and 1, which is exactly what we need for the application of stirrup. Furthermore, if we apply a 2-tone pulse, where the frequency small omega s is in resonance with the transition 2 to 1, and small omega p is in resonance with the transition 0 to 2, and we perform rotating wave approximations by neglecting the fast oscillating terms, and the terms oscillating with G are neglected in ultra strong coupling regime, then we have the ladder configuration and we have exactly the stirrup Hamiltonian. Okay, but this is this is the ideal case, just for the illustrative purpose. But anyway, for our simulations and analysis, we use the full system without any approximation. And in fact, we get more information from the non-idealities. In fact, the presence of noise disturbs everything. So it induces fluctuations in the energy levels 0 and 1, and also causes coupling between state 2 and 3, and couplings between the states 0 and 1. In the figure right here, we plotted the populations for the 4 levels, and we see that even if there is a small amount of noise present, the state 3 gets populated. And this is actually useful for detecting the correlations between the noise. And again, like the previous work, we use the similar noise classes, but here the noise are temporal and spatially correlated. And also here we included the uncorrelated Markovian noise. So in total, we have 6 noise classes. And this is the result. So again, we have the 3 messages. The neural network is able to distinguish very well the non-Markovian and Markovian noise. The second message is it is also able to distinguish the spatial correlations within the non-Markovian class. And the third is it is able to distinguish also the spatial correlations of the Markovian class, of course, with certain amount of errors. And overall, we can get a classification accuracy of 86%. Okay, so in summary, we saw that it is possible to combine quantum control and machine learning to detect noise correlations in multi-level quantum systems. We exploit the sensitivity of stirrup or sit-up protocol for detecting noise correlations. In 3-level system, it is possible to distinguish very well the non-Markovian and Markovian noise. And it is also possible to distinguish the energy correlations in the non-Markovian class almost with 100% accuracy. But here it fails to distinguish the energy correlations in the Markovian class. Instead, for the two qubits sensor, the neural network is able to distinguish also the space correlations in Markovian noise class with around 80% accuracy. Now let's move to the third and final work, which is machine learning approach for detection of noise Gaussianity in quantum systems. So until now, we did noise classification based on their correlations. And so the next question that comes, that what is the statistical signature of the noise sources? Is it Gaussian, like it is often assumed in open quantum system problems, or it is non-Gaussian? So a stochastic process is said to be Gaussian if it can be fully characterized by its mean and 2-time autocorrelation function. In this case, all the higher order cumulants vanish. And one of the examples of this kind of noise is electromagnetic noise. Instead, for the non-Gaussian noise, this is not the case. The higher order cumulants are non-zero, and they can also have relevant effects in the decoherence. And some examples of this kind of noise are impurities and 1/f noise in superconducting and semiconducting devices. So note that noise with the same power spectra can be Gaussian or non-Gaussian. For example, random telegraph noise and Ornstein-Uhlenbeck noise, both of them have same 2-time autocorrelation function, thus the same spectra, but RTN is non-Gaussian, while OU is Gaussian. So they have different effects on the system. For the RTN, the important parameter is the switching rate, while for the Ornstein-Uhlenbeck noise, the important parameter is the inverse of correlation time. Here we plotted one realization of both type of noise. And in this work, our goal is to use a single qubit as a probe together with machine learning to detect Gaussianity and characterize these noises. So here we considered qubit, which is coupled with n number of bistable fluctuators, each mimicking random telegraph noise. The qubit Hamiltonian is given by hcis, where epsilon is its energy and delta is the coupling, and the h noise is given by the random telegraph noise multiplied by their coupling, sum over all random telegraph noises coupling by multiplied by their coupling strength. And here we assume that the random variable xt switches between two values, plus and minus 1. And the switching rates between these two values are gamma over 2. Now, for simplicity, we considered pure dephasing case. So we set delta is equal to 0. And for n identical fluctuators, so if the couplings of the fluctuators are the same and their switching rates are also the same, then the analytical expression for the coherence of the qubit evolving under n identical RTN sources is given by this expression here. And now something interesting happens. If we increase the number of fluctuators n and simultaneously decrease the parameter g, which is the ratio between the coupling and the switching rate, such that ng square is equal to constant, then the cumulative effect of all the RTN sources becomes equivalent to Ornstein-Uhlenbeck noise, which is a Gaussian process. And the expression for the coherence reduces to a form like this. And this is the exact similar form if we consider that the qubit evolves under an Ornstein-Uhlenbeck noise with mean 0 and exponential correlation time. So here we analyzed two scenarios. First, that the environment is composed of finite number of identical fluctuators. Here, n equal to 1 means that the noise is strongly non-Gaussian. And as we increase the number n, it becomes more and more Gaussian. So here, n acts as a measure of Gaussianity. So the machine learning task is to infer two parameters, the number n and the switching rate gamma, by observing the temporal evolution of the system. And in the second scenario, we considered a hybrid environment where the qubit, where one fluctuator is strongly coupled with the qubit, while the rest is weakly coupled. And the cumulative effect of the weakly coupled ones become equivalent to an Ornstein-Uhlenbeck noise. And in this case, actually, the environment has both Gaussian and non-Gaussian components. So in this case, the machine learning task is to infer 4 parameters: the coupling strength of the strong fluctuator, VRTN, its switching rate, gamma, and the coupling of the equivalent coupling of the weak fluctuators, VOO, and its inverse correlation time, 1 over tau c. And these are the results. Actually, here we measured the average of sigma x at discrete times during the evolution of the system. And the neural network here predicts the 2 parameters, n and gamma. And in the pictures right, here in the y-axis, we plotted the parameters that we want to estimate, n and gamma. And in the x-axis, we plotted the number of test samples. The black dots here represent the target values, while the orange dot is are the predicted values. And we can see that the neural network is able to predict the value of n until 9, around 9. But after that, it fails to estimate the value of n, because in this case, the evolution of the qubit becomes very similar to the Gaussian evolution, and the neural network is not able to distinguish it anymore. And instead, for the gamma, the switching rate, the neural network is able to estimate it quite well. For the second scenario, instead, we try to estimate the 4 parameters, as I mentioned, and we see that the most difficult parameter to estimate is the gamma, the switching rate. Instead, for the other parameters, we see that it is able to estimate good enough. So in summary, here we saw that we developed a data-driven framework for characterizing Gaussian and non-Gaussian noise using a single qubit as a probe. We saw that using supervised learning, it is possible to infer key noise parameters. And we saw that the potential of machine learning as a powerful tool for noise spectroscopy. And for Outlook, we are trying to apply unsupervised learning for the first 2 works. And for the last work, we are also doing the similar analysis on 1/f plus 1-Shockley couple RTNs. And these are the publications that I had during my PhD. The last 2 works are not included in my thesis. Thank you for your attention.